Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will discuss about some of the very fundamental aspects of soft magnetic materials. In the last couple of classes we have elaborately discussed the microstructural aspects of hard magnetic materials as well as the soft magnetic materials, how to tune the microstructure in order to achieve either in the hard magnetic properties or along the direction of the soft magnetic properties. And we have seen that one of the very important aspect in case of soft magnetic material is that the grain size or the crystallite size, because if we have to produce a alpha iron rich nanoparticle that is embedded in a softer matrix with a very high permeability, then the crystallite size or the grain size is also important. So, today we will continue that discussion with the last class. So, the same plot I have shown you in the last classes. So, you can see here this is the effect of grain size on the coercivity value. In a soft magnetic material, we try to achieve the lowest coercivity values. Now, coercivity has a limit for soft magnetic material, that is 10 to the power 3 ampere per meter, and it should be less than that. Okay. Now, for transformer steels we use iron silicon steels, and they have quite a larger grain size like CRGO steels and so on. So, this is 10 micrometer and this is 100 micrometer. So, in this larger grain size regime, the size, the domain wall that has a thickness of delta wall and the grain diameter is larger than the domain wall. So, it basically says that I may have multiple domain, magnetic domain inside a grain. Okay. And now, if I decrease the grain size, then automatically the coercivity increases, means it is going towards a harder magnetic side. Okay. Now, if it reaches and goes above 10 to the power 3 ampere per meter also. However, here the relationship lies that H c is proportional with the 1 by d, means I decrease the grain size, the H c increases, right. So, the trend is there are two type of trend one can notice. So, type 1 trend and type 2 trend. Now, in type 2 trend, that below a certain grain size, which is somewhat in the scale of, let us say this is 10 nanometer and this is 100 nanometer. Okay. Below 100 nanometer scale, further the coercivity decreases and it scales with basically that d to the power 6. So, the smaller the grain size, the lower the coercivity value. Okay. So, in this particular case actually the interesting feature that all these amorphous precursors magnet or let us say nanocrystalline soft magnet, they lie in this very small coercivity value of 1 to 10 ampere per meter. And this is a bigger achievement in some case, where you can see that the wall thickness, means the Bock wall or the domain wall thickness itself is larger than the grain. It basically says that individual grain act as a single domain, and this is a very benefit. And so, the grain boundaries actually that impede the domain wall motion, and that is one of the disadvantages, and therefore, the fine grain material are magnetically harder than the large grain. Whereas, when we reaches to this side with a very low coercivity value, then the very small size where d is less than 100 nanometer, the domain wall thickness exceeds the grain size and the grain size length scale are irrelevant to the domain wall pinning. Okay. So, almost we can rule out the domain wall pinning phenomena that is available in a silicon steel. So, this is a very nice concept that we can improve the soft magnetic properties by designing these nanocrystalline and amorphous matrix magnetic alloys. Along this direction, we need to think about that what are the effect of a multi-domain or a single domain in a grain. So, let us say in a arbitrary scale, I show you here, this is a particle size versus coercivity. So, I may have some optimized situation where in this side, so if I increase the grain diameter, then HC basically decreases. So, it basically proportional with 1 by d, whereas in this case when I decrease the d, then coercivity is also decreases. Okay. So, in this case, since the domain wall has a lower thickness than the grain diameter, I will have a chance to have a multi domain in a single grain. Okay. This is the condition, whereas if I am in this side, then I may have a single domain in a grain that I can achieve. Now, here let us say the situation is shown that if the grain size become very small, then I have, let us say these are the atomic magnetic moment in an atom, the resultant moment in an atom. So, the grains may be crystallographically oriented in different ways. So, I have also the magnetic domains that are oriented in a paramagnetic fashion, and this is a nature we call it as a super paramagnetic behavior. So, below certain critical size of the grain size, then grains with a single domain which are randomly oriented. So, magnetic domains are oriented along with the grain orientation. So, this is a super paramagnetic behavior, whereas above this scale we may get a stable single domain. However, there is some benefit of this super paramagnetic type of behavior, we will talk in the next slide. So, super paramagnetic behavior is actually linked with that the elementary magnetic dipoles, these are the elementary magnetic dipoles of an atom, and they are oriented parallel inside a domain or inside a grain, because I have a single grain and inside that grain I have a single domain. Okay. So, in that case the atomic or elementary dipoles that are oriented along a same direction, however, the orientation of the magnetic moment of the particles are random. So, here if I draw a net moment of a particle, then they are oriented in a paramagnetic nature. Okay. So, random orientation of the magnetic moment, whereas I can also produce the same kind of microstructure. However, what I need that individual grains or the domains here are in the equal distance. Okay. They are aligned in equal distance, as well as the magnetic moment are aligned in the same direction of the individual grains or individual domains, because I have a single domain in a single grain. Now, in that case you can see now the material behavior become ferromagnetic. Okay. So, the super ferromagnetic particles that are equal in size, because the individual domain should have the same number of atomic magnetic spins that are oriented in the same direction. So, that will allow a dipole-dipole interaction in a magnetic coupling between the particles that has to occur, and orientation of the magnetic moments or particles are all in parallel in a particular direction. So, this is a very interesting phenomena in a nanocrystalline soft magnetic material, where I can produce a very fine nanostructure with a super paramagnetic or super ferromagnetic type of behavior. So, on the other hand, all these magnetic material that will undergo the phase transformation, and we know about the phase transformation which I have discussed before the shape memory concept, and there the concept of phase transition is not too different, but here in a magnetic material the important aspect that upon application of a magnetic field whether there is any phase transition will occur or not. And the phase transition, as we have discussed, that there are two types, a first order or second order type of transformation, and the first order transformation are characterized that the magnetization value which is basically the first order derivative with the applied field. So, delta G by delta H at a given temperature, and if there is a discontinuity we call it as a first order. Now, let us say I can have del square G by del H square, where the second order derivative of the free energy that become a shows us a discontinuity with the applied field like a susceptibility, then we can call it as a second order magnetic transition. However, in a broader category the first order as well as the second order transition we can think about. In a second order transition it basically occur like a iron, nickel and cobalt, which is a characteristic of a TC. So, like a Curie temperature you can see that there is a disappearance of the magnetic behavior. Okay. So, that is a typical characteristic of a second order transformation. However, if the Curie transition occur over a wide range of temperature or a very sharp at a given temperature, then this behavior will be different. So, the first order transition will show us a behavior with a ordered disorder type, or maybe it may occur due to some sort of structural change, where the structural change I am talking about sometimes the crystallographic structure may be changed or the order parameter that shows us a jump. So, in case of ordered disorder transition here I have manganese arsenide, or let us say the UO2, that is uranium oxide. So, that shows a ordered disorder type of magnetic transition, whereas in case of a structural change the free energy which is basically a function of a order parameter eta. So, this order parameter will decide whether the structural change is related with a magnetic transition or not. So, let us say order parameter shows us a jump at a critical temperature TCR. Okay. So, in that case the crystal structure does not change, but the order parameter has changed. So, let us say in case of iron system, or let us say manganese platinum system, such kind of change has been observed, which is also a first order transformation. Whereas, when this order parameter has a very close value around 0 and temperature is greater than the critical temperature, or order parameter has a value which is a non-zero quantity below a critical temperature, and that case the crystal structure will be changed. Like in a cobalt I have alpha to beta transition, or maybe in case of iron I have alpha iron that transform into a gamma iron. So, this is a crystallographic change. Okay. So, crystallographic change is also linked with a magnetic property change. Okay. So, like the susceptibility will change, the remanence magnetization will change, and all these properties will change, and these are linked with the structural change that causes a magnetic property change, and these are called as a first order transition. So, the onset of a magnetic ordering, or let us say the ferromagnetism, that result due to a smaller or larger distortion in the crystal lattice, and in many cases without any crystal symmetry change, it also related to the dependence of the exchange energy of the interatomic spacing. Means, if there is a crystallographic change that occur, then there will be net a pair of the atoms, the distance will change because there is a crystallographic change, or other hand I may have a structural ordering change where crystal structure does not change, but the pair has changed. So, this ordered disorder transformation which is basically I have represented here, where ferromagnetic material goes to a paramagnetic material or vice versa, or let us say a antiferromagnetic material that goes into a ferromagnetic transition, that can be a order disorder transition. So, here let us say the manganese arsenide, it also shows a transition around 318 K. So, the main importance here, that if the exchange energy dependence on the interatomic spacing is rather strong. So, let us say I have 2 atom and this interatomic spacing is the exchange energy is very much dependent on this interatomic spacing, then rather strong, then the first order phase transition will be observed instead of a usual second order one. Okay. So, this exchange interaction is one of the very much important aspect to classify whether it is a first order or it is a second order type of transition. Now, once again, like hard magnetic material which we have discussed about the exchange coupling of the interatomic exchange coupling, in case of soft magnetic material too, the similar phenomena actually occur. So, we also choose different alloying elements based on that. I have plotted here the atomic separation distance, that is d, divided by the diameter of the 3D orbital. So, this is the x axis, and in the y axis this is the exchange interaction energy. So, J exchange interaction, this is the exchange energy, interaction energy, and here in the x axis we have basically the ratio of the atomic separation distance with the diameter. So, iron lying here, cobalt lying here, nickel is lying here. Now, we can take this point and think about whether if I add let us say cobalt, whether it is going to increase or some other element that will basically decrease the exchange interaction energy. This is the important aspect of this Brett-Slater curve. So, the atomic moment due to a spin vector s on a nearest neighbor site coupled by a nearest neighbor exchange interaction gives us a potential energy change. So, this potential energy is linked with the exchange energy multiplied by the spin vector with its nearest neighbor. So, the exchange energy that become greater when parallel alignment of spin is favored. So, I am going to increase the exchange energy only when there is a chance of the spin that is favored for a parallel alignment. Okay. So, this exchange interaction that can be used from this mean field theory to estimate the Curie temperature. We can estimate the Curie temperature by Z, which is basically the nearest neighbor coordination number with the exchange energy as well as S into S plus 1, okay, divided by the Boltzmann constant. So, we can simply estimate the Curie temperature by only this exchange interaction potential from this Brett-Slater curve. So, this is something very much interesting, and I can show you 2 different examples in which case there is a iron rich alloy and other case I have a cobalt rich alloy. Now, in case of this Brett-Slater curve, I have iron. Okay. So, from 1.6 if I basically add cobalt, then I am going to increase, that is J delta J plus. Whereas, if I have let us say a cobalt, now the X and add iron there, then the increase of the energy is very less. You can see that the increase of this energy of delta J, that is very less compared to a iron rich alloy. Okay. So, such a fluctuation of the exchange interaction will change the interatomic distance in iron rich alloy, which causes a more fluctuation than a cobalt rich alloy, which has a lower fluctuation value. So, this is one of the very important aspect of choosing alloy composition and choosing this atomic pair, which should favor the exchange interaction with the proper spin alignment. Now, for a exchange coupled magnetic nanoparticle, now I am not talking about basically the atomic level exchange interaction, but in a magnetic domain interaction, where the red color domains are shown as a hard magnetic domain which is surrounded by some soft magnetic domain. Okay. And now, there is a dipole interaction between the soft magnetic domain and the hard magnetic particle, that is obvious. However, if I align these, if I wish to align the hard magnetic domain, then also or otherwise if I have to align the soft magnetic domain, I also have to align the hard magnetic domain. So, because there is a exchange coupling between these two magnetic domains. Okay. So, in that case the pinning is done by these harder domains. Okay. So, the material may consist of some amorphous matrix with nanocrystal. Amorphous matrix is a soft magnetic domain, and let us say I have alpha iron which is a harder one, and so hard and soft magnetic nanoparticles may be also present. So, the soft magnetic particles that are let us say super paramagnetic in nature, super paramagnetic means they are oriented randomly. So, I have smaller domains which is oriented this way, and other one is in this way, super paramagnetic that I have just discussed few minutes ago. So, super paramagnetic and located directly adjacent to the hard magnetic nanoparticles, and the dipole moment of the hard magnetic particle forces the magnetization of the soft magnetic particle in the same direction. So, I can achieve a super ferromagnetic type of behavior by adding this kind of harder magnetic nanoparticle inside it. So, consequently the whole moment around the hard magnetic particle become oriented magnetically in the same direction. So, we can achieve a super ferromagnetic type of behavior by aligning these small magnetic domains in the same direction. So, this is one of the biggest advantage of this kind of nano composite microstructure. However, we can also think about some sort of core shell type of microstructure. What I want to mean that I have a nanograin or nanocrystal and outside there is a shell. So, this shell is a soft magnetic nature and the inside it is basically hard magnetic nature, and these are the soft magnetic spin that are aligned along the direction of the hard one, or otherwise I have a hard magnetic core outside shell and a soft magnetic core inside. So, this could be the two different cases, and the interesting thing here that I have added this soft domain and hard ferromagnetic domain together, and the resultant exchange coupled magnet can show us such a hysteresis loop or a spring magnet type of behavior with such a differences in a zigzag type of our curve behavior. And this is a graphical representation that I have shown you, that the hysteresis loop of a soft and hard ferromagnet with such kind of core shell microstructure could give us some interesting hysteresis loop with a possible combination with a exchange couple or exchange spring type of magnet. So, by microstructure from individual domain we can produce some core shell type of microstructure, and that could be beneficial for us to produce different magnets which has a very different hysteresis loop than the conventional nanoparticle or nanocomposite magnetic material. So, these are really the very interesting functional material that can be generated. So, one of the example I like to show you here, this is a core shell type of microstructure with a cobalt oxide with a cobalt cluster. So, I have inside which is a cobalt and I have cobalt oxide which is present on the outside of the as a shell. So, this is typical core shell type of microstructure. Now, all these different magnetic nano composite, this is also a nano composite, and all these type of different nano composite one can classify into these major, let us say 4 categories along with these other 2 one. So, the first one here, the type A, this is also a type A. Here you can see that the material include a ideal ultrafine particle system with interparticle spacing large enough to approximate the particle as non-interacting in nature. So, the particles are far away and there is no exchange interaction between the particles. Okay. So, and I have produced such kind of nano composite. On the other hand, I can produce such kind of core shell type of microstructure that I have just shown you here. So, I have a core and I have a shell, and this is a ultrafine particle with a core shell morphology. On the other hand, I can also produce a nano composite that are composed of a small magnetic particle embedded in a chemically dissimilar matrix, and the matrix may or may not be magnetoactive. So, either in one case this could be active or maybe non-active. Now, I can also have a chance that is a type D type of microstructure. Here you can see these are some nanocrystalline structure that has two phase, one phase here inside and the black dotted curve, portion is the other phase. So, I have phase 1 and I have phase 2. So, this phase 2 could be let us say either magnetic and the nanocrystalline are the distinct phase from the matrix, or maybe both the portion have from the same type of material. Okay. So, this is one of the very interesting microstructure development in case of nano composite material. However, one can also derive some microstructure along this direction of D, that I may have a ferromagnetic nanograin inside and that is surrounded by a grain boundary phase which is weakly ferromagnetic in nature, or maybe I may have a very strong which ferromagnetic nanograins. Here this is a ferromagnetic nanograin, but some carbide is present at the grain boundary as a continuous phase that pinned the microstructure. So, that basically makes to orient or align the microstructure more difficult. So, that is the pinning action that in a magnetic material. So, you can see such kind of wide range of metallurgical aspect that is possible for developing several types of soft magnetic material. Now, one part is sure that for transformer core we need soft magnetic material. There is no doubt about it, because we can achieve a low core loss and eddy current loss and so on, and magnetic shielding material is also possible. The tensile stress transducer can be possible, or let us say transverse filter can be also possible. So, this is a typical example of such kind of 60 hertz transformer, where I have the cores and they are placed together, or let us say the ribbon that is wound in a cruciform distribution of a transformer application. Okay. So, here these are the ribbon that is spinned to or wounded, so that we can make such kind of transformer. However, inductive components, that is switch mode for power supplies, or let us say magnetoelastic transducer or magnetic springs or magnetic head for data storage application. Here also we have application of the soft magnetic materials. And another interesting amorphous magnet, since the flux we can produce or permeability can be very high. So, we can use this as a magnetic shielding. So, let us say I have developed a laptop or computer, and that should be magnetic shielded from the outside magnetic flux, so that the magnetic stored information data should not be lost. Okay. So, for that kind of purpose we can produce such a plate of amorphous magnet with a very high permeability value. I can put this magnetic plate on a top of a laptop, so that it could be properly magnetic shielded, or one can produce this magnetic York that is made of some BMG plate. BMG means bulk metallic glass, for a prototype linear actuator, So, there is a large application areas of these soft magnetic material and on today's concept. We have generalized and tried to explain all the different fundamental aspects of different hard and soft magnetic materials with discussion the latest developments of magnetic material with let us say exchange coupling between atoms, magnetic moment and exchange interaction between different nanograins, and how we can achieve many different types of functional and functional magnetic properties with core cell type of microstructure. So, with this we complete the discussion on hard and soft magnetic materials, and in the next week we will start with a new discussion topic. Thank you very much.